Hello everyone. In this experiment, we are going to explore RLC circuits and how they function as filters. Filters are everywhere in physics and engineering, from audio systems and radios to signal processing and communication circuits. By carefully combining resistors, inductors, and capacitors, an RLC circuit can be designed to allow certain frequency to pass through while blocking others.
In this video, we have three objectives. First, we aim to understand the fundamental principles of RC and RLC circuits, with emphasis on how low-pass, high-pass, and band-pass filters operate in practical applications. Second, we will experimentally measure the input and output signals of RLC circuits using an oscilloscope and plot their frequency response curves. Finally, we will explore the physical meanings behind RLC circuit by investigating key concepts such as resonance frequency, bandwidth, and the overall frequency response of a system. To clearly observe the filtering action, we need a signal whose frequency can vary continuously over a wide range. For this purpose, we can use voltage to control frequency such that the frequency varies with changes in the input amplitude. Let's take a look at how this signal is generated.
To generate a voltage control frequency signal, we use two function generators. And the output of the first function generator provides a control voltage, and then which is connected to the frequency input of the second function generator. And as a result, the frequency output of the second generator varies according to the input voltage. This is known as the voltage control frequency. And then the output voltage from the first generator is connected to the channel 1 of the oscilloscope. And then the voltage from channel 2 is connected to the circuit and then connected to the oscilloscope, the channel 2 of this oscilloscope. But because we have to demonstrate how the amplitude and offset affect the frequency, we first connect it directly into channel 2. First, let's observe the effect of the amplitude. So here the amplitude is at its minimum, and we can see that the frequency range is very, very small. It's kind of like from 900 to 1000 Hertz. So the range is pretty small. But if I increase the amplitude, you can see that here a part of the frequency gets denser, and that makes higher frequency. So when I turn to the maximum amplitude, you can see that the frequency range is from like 2000 Hertz to about 900 Hertz. So the range gets wider. So in conclusion, the amplitude controls the frequency sweep range, not the absolute frequency. And then let's talk about the effect of the offset. So if I pull this offset, you can see that the total frequency increased dramatically. And then if I increase the offset, although the shape of this frequency will not change, the frequency itself is changing. So we can see that at the maximum offset, the frequency gets very, very low. So in conclusion, the DC offset shifts the frequency range, but it does not change the sweep range.
Okay, so the second function generator is connecting to the whole circuit, including the capacitor and the resistor. And the channel 2 of the oscilloscope is across this capacitor. So here we can see that the high amplitude of the first function generator is corresponding to the low frequency of the second function generator, and the low amplitude corresponding to the high frequency. So we can see here this part is getting restricted. So when we change it to XY mode, we can see that here high amplitude of the first channel 1, first function generator, and here it's corresponding to the low frequency, and the other side is the high frequency. And if I shorten the range of it, then turn on the offset, then we can see which part we want to observe. Like for example, here I want to see here, then turn it back to YT mode. So that's where I want to see, and therefore this is our experimental results. Alright, so now if we want to find the cutoff frequency, we can use this offset to find the maximum value of the stick. For example, it's here, about here. Then we can see how long it is. Like for example, here's about maybe 3 unit length. Then we times 1 over square root of 2, and it's about 2.1. We shift it. Maybe here we change it back to YT mode and use the measure to see it. So here this frequency is about the cutoff frequency that we want to find. In a typical low-pass configuration, the output is taken across a capacitor, and at low frequencies, the capacitive reactance is large, so the capacitor behaves almost like an open circuit. As a result, most of the input signal appears at the output. At high frequencies, however, the capacitive reactance becomes very small. So the capacitor then provides an easy path for the signal to ground, significantly reducing the output voltage. This frequency-dependent behavior causes the circuit to act as a low-pass filter. The transition between the pass region and the attenuated region occurs around the cutoff frequency, which is determined by the circuit parameters. Using this formula, we can calculate the expected cutoff frequency.
Now, let's examine the experimental result of the low-pass filter. From the oscilloscope display, we can observe that at low frequencies, the output waveform closely follows the input waveform, indicating minimum attenuation. As the frequency increases, the output amplitude gradually decreases, demonstrating the expected low-pass behavior. The maximum output voltage measured in this experiment was 1.88 volts. At the cutoff frequency, the output voltage dropped to approximately 1.32 volts, which is close to 77% of the maximum value. Based on this criterion, the experimentally determined cutoff frequency was approximately 4,700 Hz. The calculated theoretical cutoff frequency is 4,825 Hz. Comparing the experimental and theoretical values, the error is approximately 2.6%, which indicates good agreement between theory and experiment. This confirms that the observed frequency response of the circuit is consistent with the expected behavior of a low-pass filter.
Okay, so for a high-pass circuit, that's just basically the same as a low-pass one. The second function generator also connects the whole circuit but this time the oscilloscope and the channel 2 should connect across the resistor. Then here's how it should look like. And as for the measurement, we can use the same method as what we use for low pass 1.
In a typical high-pass filter configuration, the output is taken across the resistor. At low frequency, the capacitive reactance is very large. This means the capacitor effectively blocks the signal, resulting in a very small output voltage across the resistor. As the frequency increases, the capacitive reactance decreases. At high frequency, the capacitor behaves almost like a short circuit, allowing the signal to pass through the output. Similar to the low-pass filter, the transition between the attenuation and transmission occurs at the cutoff frequency, which is determined by the same formula. Next, let's examine the experimental results of the high-pass filter. From the oscilloscope display, we can observe that at low frequencies, the output signal is strongly attenuated, indicating that low-frequency components are effectively blocked. As the frequency increases, the output amplitude gradually increases, which is characteristic of a high-pass filter. The maximum output voltage measured in this experiment was approximately 0.82 volts. At the cutoff point, the output voltage dropped to about 0.58 volts, corresponding to roughly 70.7% of the maximum amplitude. Based on this criterion, the experimentally determined cutoff frequency was approximately 7,200 Hz. The theoretical cutoff frequency is 4,825 Hz. Compared with the experimental value, this result is a relatively large error of approximately 49%. This discrepancy can be attributed to several experimental factors. First, in a high-pass configuration, the output is taken across the resistor, making the measured signal more sensitive to loading effect from the oscilloscope input impedance. Second, parasitic capacitance from connecting wires and measurement probes can significantly affect the circuit behavior at higher frequencies. As a result, the experimental cutoff frequency appears higher than the theoretical prediction. Despite the large error, the overall frequency response still clearly demonstrates the expected high-pass filter behavior, confirming the qualitative operation of the circuit.
Okay, so the circuit for bandpass circuit is like this, with the second function generator connecting the whole circuit and the channel 2 of the oscilloscope across the resistor, just like high-pass 1. And this one is inductor. And this circuit that is a combination of high-pass and low-pass. Just like we can choose a certain frequency that could pass through. And we can change these three electronic components to have various certain frequency that could perform on the oscilloscope.
In practice, a bandpass filter can be realized using an RLC circuit, where the compact effect of the resistor, capacitor, and inductor can determine the frequency response. At low frequency, the capacitive reactance is large, which limits the signal transmission, and at high frequencies, the inductive reactance becomes dominant, again reducing the output signal. However, at certain intermediate frequency, the inductive and capacitive reactance balance each other. This condition is known as resonance. At the resonance frequency, the impedance of the circuit is minimized, and the output voltage reaches its maximum value. As a result, the circuit strongly transmits signal only within a narrow frequency range, forming a bandpass characteristic. The resonance frequency can be calculated using this formula. Finally, let's evaluate the experimental results for the bandpass filter. From the oscilloscope display, we observed that the output signal reached its maximum amplitude near the resonance frequency, while it is attenuated at both lower and higher frequencies. The lower cutoff frequency FL was measured to be approximately 6,540 Hz, and the upper cutoff frequency FH was approximately 7,120 Hz. The bandwidth of the bandpass filter is defined as the difference between these two cutoff frequencies. Using the experimental values, the bandwidth delta F is 7,120 minus 6,540, which equals 580 Hz. The center frequency of the bandpass filter is given by the average of the two cutoff frequencies. Experimentally, the center frequency F0 was determined to be approximately 6,830 Hz. The quality factor or Q factor describes how sharply the circuit selects a narrow frequency range. It is defined as the ratio of the center frequency to the bandwidth. Using the measured value, the Q factor is F0 divided by delta F, which gives a value of approximately 11.7. The theoretical resonance frequency of the circuit is 5,030 Hz. Comparing the experimental and theoretical values, the relative error is approximately 35.7%. This discrepancy can be attributed to non-ideal circuit components, parasitic resistance, and measurement limitation at higher frequencies. Despite this deviation, the experimental result clearly demonstrated the expected bandpass behavior, as well as the physical significance of resonance, bandwidth, and quality factors in an RLC circuit. In this experiment, we investigated the frequency selective behavior of RC and RLC circuits by constructing and analyzing low-pass, high-pass, and bandpass filters. Through oscilloscope measurements and frequency sweeping, we successfully observed cutoff frequencies, resonance behavior, bandwidth, and quality factor. The experimental results show good qualitative agreement with theoretical predictions, and deviation can be explained by non-ideal components and measurement limitation. Overall, this experiment demonstrates how fundamental circuit elements can be combined to control signal frequency response in practical applications.